Time for our next program, and that is acid soils, really. Can there be too much K? So to provide the presentation is Dr. Dave Franzen. Dave was not able to be with us today. He had another program that he's attending, but he was able to produce a video. So we'll view the video, and of course Dave is not present, so we won't be able to have a Q&A session. But I think most of you know Dave. And if there's some questions that are generated after viewing his video, please feel free to contact him directly. Dave does serve on our planning committee, as I mentioned yesterday, and he's provided a lot of support both in planning the program and presenting the program and helping us solicit other soil scientists from across the region to be on our program. So we really appreciate Dave's wonderful work that he's done to help support our Advanced Crop Advisor Workshop. Dave is originally from Illinois, and he received his PhD at Illinois. He worked in private industry for many years, and so he had a really good foundation of some of the practical things practical problems and challenges that guys have with plant nutrition and soil management. He came to NDSU in 1994, and he's currently a professor at NDSU and, of course, our extension soil specialist.
Hello, my name is Dave Franzen. I'm an extension soil specialist at NDSU, and I've been invited by the Advanced Crop Advisors to talk to you about information I have about acid soils in the region, and also perhaps excessive potassium rates. So first, acid soils. Really, I think most people in the region have grown up thinking that all of our soils had pHs above 7, and we'd never have to really worry about acid soils, but that's not the case. So all of our crops grow really well when we have pHs above 5.5, exception perhaps alfalfa, which likes a pH even above that, 6.5 or better. But here's a legume growing in pH of 5.5. The nodules are usually found within a couple inches of the surface with few exceptions. So everything is fine and it's growing really well. But if we have a legume growing in the soil after maybe 20 years of long-term no-till and urea has been applied near or at the surface during that period of time, we can have the stratified acid pH. We've seen it as low as 4, and if you get west of here into Montana and eastern Washington and parts of Idaho, it can get lower than that. So that's really pretty serious stuff. So there's no nodules. Plant growth is really horribly reduced. So how does this happen? I mentioned the ammonia fertilizers. Just plants growing shoot out acids out of their roots, and then if we put on nitrogen fertilizer, and it's usually ammonia based, anhydrous ammonia, urea, the 3/4 of the nitrogen that's in UAN, it's all ammonia based. Manure is ammonia based, and green manure is ammonia based. So almost all of our fertilizer inputs are ammonia based, and when that happens, there's a process called nitrification, and we've talked about that in other programs in a different context, and that's the process where the bacteria take the ammonium nitrogen, and in the presence of water, they oxidize it to nitrate, and hydrogen is given off. Hydrogen, not hydrogen gas, but hydrogen ions. And hydrogen ions are what we measure when we measure soil pH. That's the measurement we're taking. In no-till, most of that nitrogen is applied at or near the soil surface, and there's little soil mixing. And so all of that acidity is interacting with only a couple inches of soil. In conventional till fields, of course, you're mixing it, and this process goes on in conventional till, and eventually we're going to have to talk about this with conventional growers, but because of the concentration, we're talking Most of the problems we've seen so far have been in long-term no-till fields with the stratification. If the soil doesn't have any free lime carbonates, then the change in pH is relatively rapid, and then the pH acidity is stratified at the surface. And we'll talk about all that here in a second. So how does that buffer the soil against acidification, or how does that soil resist acidification? Well, soils with pHs less than 7 have no carbonates mixed in with the soil, or at least at the surface depth that we're measuring here. And when acidity is introduced, the pH of the soil decreases, and the decrease is faster in low CEC soils like sands and soils dominated by illites and particularly kaolinite. Here's the approximate CEC of soil clays, smectites, which have more. Well, I'll show you a map here in a little bit. But anyway, smectites have a fairly high CEC, but illites have only about a third of the CEC of smectites, and kaolinites have even less. And so soils that have these are much more susceptible to development of acidity faster than soils that have a lot of smectites in them. Soils with pH greater than 7 have carbonates, and I've seen the range from 0.1% to over 30% by weight in the top 6 inches or so. And oftentimes those carbonates are even greater with depth. So when acidity is introduced, the pH of the soil stays the same because of this reaction. The acidity, the hydrogen ions, react with the CO2 or CO3, the carbonates, and that produces water and CO2, and there's plenty of the carbonates left to maintain the pH. For example, 1% calcium carbonate equivalent in the surface 6 inches of soil is 10 tons of calcium carbonate equivalents. So there's huge amounts. And so the pH can stay the same for quite a long time. And the greater the amount of lime, the greater amount of time that soil is going to stay the pH it already is. So what's the deal about acidic pH? Why is that a problem? Why can't plant withstand it? Well, there are two things that we've seen already in the state. One is aluminum toxicity. There's aluminum in all of our soils. Remember that the clays are sheets of silicon oxide and aluminum hydroxide. Well, that aluminum doesn't go anywhere as long as the pH is, certainly 5.5, or there's a little bit solubilized below that, but it doesn't really get serious until you hit about a pH of 5. So when that happens, the aluminum ions go into solution, and as aluminum frees up, it also splits water and attaches to hydroxides, and this frees up more hydrogen ions and acidifies. The rate of acidification increases even more. So that becomes toxic to the plant when aluminum ions are greater than 25 part per million. First thing that happens is aluminum can tie up phosphate, and so the early toxicity can actually look like a phosphate deficiency. But what you see as the concentration increases is the roots become abnormally shaped because the aluminum plugs it up. It plugs up all the pipes inside the roots, and certainly the root mass is also reduced. And then manganese toxicity. Manganese becomes really soluble, and that's been identified in North Dakota as well, as it travels through the plant and messes up processes physiologically within the plant. So this is an image from Ryan Beto, our Extension Regional agronomist from Dickinson, and he's been working on this a few years, and we see these patches all over the place in the Southwest. So here's some wheat that's definitely hurt by aluminum toxicity. So it's really not going to amount to much. This is aluminum toxicity in canola. The height of the plant really isn't the story here. See how many more leaves we have? We don't have as many leaves here. Plant is elongated a little bit. I suppose it's trying to grow out of this. But the root system itself, with no lime applied and a pH of 4.4, there are not a whole lot of of axillary roots, the additional roots other than the taproot here on this plant, and in here they're much more abundant, where 4 ton of lime was applied and the pH is 5.7 and the aluminum is way down to where it should be. This is manganese toxicity on canola, and this is with lime and this is without lime. pH of 4.4 again, pH of 5.7 where there's 4 ton of lime. So this is normal and this is not, and the yields here will be pretty horrible. Usually a manganese tissue test, if you get it back from the lab, normal range is from 16 to 100 ppm, but here with a pH of 4.4, it was, what, 16 times that? Almost 1600 ppm. So that's a bad thing. So how in the world do you find these low pH areas? Well, if the problem's bad enough, you can fly over it with a drone or satellite image or something like that, and the barrier areas of the field are maybe low pH. Of course, with our problem with salts and sodium in the state, it's hard to just judge whether those areas are really low pH or if they're suffering from salts or sodium. And so the end game is you really have to do some soil sampling. Zone sampling works better than grid sampling. Various parts of the landscape tend to be higher in pH or lower in pH just because of the way the water has moved over the centuries. And so I would suggest that you would zone sample. And then also, this slide, this is one of Chris Augustine's slides. I would suggest that you do a 0 to 2 inch and then 2 to 6 inch, because the 0 to 2 inch is going to be more reflective of what's the stratifying pH than if you were going deeper. But certainly just don't go with a 0 to 6 inch core. Take your core and do 0 to 2 and then 2 to 6 before you send it into the lab. Back in 1996 was the first time I found that the state of North Dakota was not uniformly high in pH. And so I took samples from every county in the state, three locations within every county, and within each location I did a hilltop or an upland, and then a slope, and then a depression within each field. And what I found is that the low pH tended to be around the Missouri River, east and west of the Missouri River, and then coming up here through Mohall. The very western edge of the state tended to be fairly high in pH, and certainly the valley did. But there's a lot of variability in here, especially in the east central part of the state. The south central part of the state also tends to be fairly low in pH, and that was 24 years ago that I was finding this, and I was finding pHs at that time as low as 4.9 in some of those samples. And so this has been going on for a long time. It's not just a really recent event. It's only because farmers have started to sample in zones that they're really kind of getting a handle on what the variability in pH is across their fields. And so this needs to continue and intensify. So intensive crop growth, the application of any ammonia-based fertilizer, including manure, results in surface soil acidification. And the remedy is liming, which is the application of any amendment that reacts with hydrogen ions that form CO2 in water. That neutralizes what we call the pH. In conventional till systems, the liming material is incorporated into the soil during the tillage passes. And I'll want to argue now and later that surface application in no-till fields is probably what we need to try to achieve. So the idea of liming in order to reclaim land is not a new idea. In the early 1900s, Cyril Hopkins, who had issues, but he was a good researcher, the southern part of Illinois was becoming abandoned. A lot of farmers were leaving because they couldn't grow anything anymore, and nobody really understood why. And so with a series of experiments and a great extension effort at that time, it became clear that liming these fields would put them miraculously back into production. And so liming in the Midwest states and the Corn Belt states is just something you do every 8 years or so. You go in with more lime, because the idea of growing these crops and applying nitrogen fertilizer, or growing soybeans, whatever, it's an acidifying process, and you have to neutralize it in order to keep the system productive. So where I was from before, Illinois is very fortunate, because under most of the state is these huge, deep limestone seams. I mean, they're really deep, and so there's quarries underneath a lot of the cropland in Illinois, and so the distance isn't that big of a problem. Limestone costs something, but it's not a trauma really to buy and haul to the field, because most quarries are within 50 miles of any farm that you can think of in Illinois. Another source of liming material are water treatment plants. Dickinson, Fargo, Grand Forks, any municipality of any size at all has a water treatment plant, and they use lime, finely ground lime, trucked in, railed in, something in order to make the sediments fall out of solution. It's a great coagulant, a flocculant they call it. And so this falls out, and then the system is dredged, and usually this stuff is just put in a landfill or piled up someplace. So it can certainly be used as a liming material. And then our greatest source in this state, in the northwest Minnesota, of any kind of liming material is sugar beet waste lime. There's not, at least in the valley, there's not the huge piles there used to be, because sugar beet growers use limestone even when the pH is 7-8 in order to alleviate Aphanomyces root rot. In Sydney, there's still piles around, so that's the source of limestone, because we have no quarries in this state at all. So wherever you get it, the next part is logistics, and so it has to be trucked to the location, so there's trucking cost. It's piled in the field, and this is, I would never recommend anybody to do this in the springtime, because you're not putting on hundreds of pounds, you're putting on tons. So each of those piles there is about 22, 24 ton. So they're piled out in the field, and then they're loaded up. So there has to be an end loader involved, and they're loaded up into a spreader. So the more moist it is, the steeper those sides and slicker those sides have to be. And then you have to play around with the dividers, maybe take the dividers off or not. There's several entities in the Red River Valley that have figured out how to spread the sugar beet lime, and so copying them, using them, hiring them, they already have the process figured out, and then it's spread in the field. And you see the dust behind there. With sugar beet waste lime, you're not going to see that dust because it has a moisture component in it. And so you may have to drive a little bit closer together with your passes, but that's easily figured out. So this is the analysis of some of the sugar beet waste lime around the Crookston, Drayton, Grand Forks, Hillsboro. They're all in the valley. The calcium carbonate equivalent, which is the equivalent of 100% dry calcium carbonate, ranges anywhere from 70 to 75%. Normally, in Sydney, Montana, we're about 60% calcium carbonate equivalent. This is really fine stuff. I didn't put 200 mesh there, but it all can go through a 200 mesh sieve if it's dry. And the moisture content hovers around 30%. So it tends to be a little wet material. You don't haul it when it's 20 below zero. So this is some work that Chris Augustine did. Put on limestone this is zero lime up here. This is 2 ton here, and this is 4 ton here. And this site was incorporated to 6 inches when it went across with a chisel plow, probably at 6-inch depth. So it was kind of mixed in that area. So where we didn't have any beet lime, the pHs were anywhere from 4.3 to about 4.5. 2 ton of beet lime increased those pHs to in the 4.7 to 5.2, and 4 tons of beet lime increased the soil pH to 5.5 and above. So this is kind of where we want to be. And again, this is what it looks like in the soil. This is 2 ton an acre. This is hauled from Sydney. Cost about $50 a ton to haul lime from Sydney to Minot, and then you have to spread it and all that. So this is what 8 ton looks. This is what 4 ton looks. So that's what it looks. And you know, we're talking some expense. It's $100 an acre. That's what, $400 an acre, $200 an acre. But if you don't do this, the land's not productive, and so you know, you don't do the whole quarter. But if there's 30 acres in the quarter that are suffering from really low pH, then you better do that, or else I don't know, put a for sale sign in the 30 acres that don't do anything, because you're still paying taxes and everything else, but it's not producing anything. It's just a waste. So this is what wheat at Minot looks like without lime in the foreground, pretty miserable. And this is a lime application that's been mixed in to 6 inches here in the background. So huge. This is back to normal wheat yields, and this is just pathetic here. So Ryan Beto and Chris Augustine are working hard to try to figure out what the effects of surface application of lime compared to working it in would be. There are some research articles that are published in respectable journals that they all conclude that surface liming, if you hit the problem soon enough, and I think we're still in that window, that surface liming can alleviate that low pH stratification in the no-till soils, and alleviate the aluminum toxicity and manganese toxicity as well. So I am hopeful that when people really grasp this and really start to move to correct it, that surface application is all we need to do. This is some information from Montana State. Montana has the same problems that we have, and have had it for a longer time than we have. They've found that you can overcome short term, like 1 year, if you know you really have a problem in an area. You can put on some pretty high rates of seed place phosphate. Here we're looking at 200 pounds of 0.460. Per acre to get to the level as 5 ton of acre lime. But it's a short-term fix, and you have to lime eventually, but this might get you by a year or two until you're financially able to take care of the pH problem with the lime application. So once you have this pH corrected, the nodules will be able to form on the plants just fine. This would be with pH of 6. Below here might be a pH that's lower than that. I put 5.0 here, but and it's possible that if it's been neglected for a long time, you still might have some low pHs. But a lot of times we have some pretty high pHs down here in the subsoil, and so the crops are able to grow just fine. All you have to do is to alleviate the pH of the surface, and you're good to go. The thing I worry about, well, there's 2 things I worry about. One of the things I worry about with incorporating the lime to any kind of depth is that erosion, wind erosion especially, is a huge problem, and it's a huge hazard. And a lot of people move to no-till and have been in no-till for a long time to avoid erosion. Also, we found, and growers have used this even before I put it in the publication, that there's a nitrogen credit for long-term no-till, and if you till the soil, that's going to be disrupted for a period of years. So one of the costs of tilling to move the lime into the soil to depth, if you feel you need to do that, is that it probably, and I haven't researched it, but this is my gut telling me what's going to happen, is that you're going to limitate that no-till benefit for probably 5 years or so. That you're going to destroy the housing this stuff lives on. You're going to burn up a little bit of residue organic matter with introducing that oxygen and destroying some of the aggregates, and it's going to take a while in order to reestablish that. So if you decide that I'm cracked and decide that you want to go ahead and apply that credit, I would urge you to put 50 pounds of N in a little strip over and above what you normally would do, and just make sure you made the right decision. If that strip is greener than the rest of the field, then you better put some more on the rest of the field. So here are some steps to remediate that acid soil pH. You just do the soil sampling, divide that surface 6-inch core up into a 0 to 2 and a 2 to 6-inch core, and have the lab run pH. And if the lab will do it, run a buffer pH on both depths. The buffer pH will give you a better idea, especially with the variance we have in clays across the state, of really how much lime you might need to apply in order to correct the pH problem. So next is logistics, lining up the lime source, scheduling the application. I would really urge you to do it in the fall, maybe after a shorter season crop like wheat or canola or something, and then apply it before freeze up, because afterward it's going to be pretty chunky. Some people have mentioned pellet lime, but I don't know. Lime's expensive enough. And yeah, pellet lime, you can get it through an applicator, but you're still going to have to put on tons. The efficiency is not, because you can either spread it with a air seeder, or not an air seeder, but a pneumatic spreader versus a spinner spreader. It just takes massive amounts in order to make it work. And pellet lime does not have efficiency. And so putting on 100, 200 pounds, it's not going to do anything for you. So that's surface acidity. So we're in a liming state now, and the deterrent right now is that we don't have any quarries, and there aren't many, if any, fertilizer companies that are really tooled up to do this. And so it's going to take an effort. It's going to take some realization that this is really a problem, and that it's going to be worth people's while to do it. And it really is worth your while, but I know that this talk itself isn't going to convince you. So I'm looking forward to the work that Chris Augustine and Ryan Vito are doing down at Minot in order to convince farmers that they really need to do something. So next I wanted to touch on this topic, and I call it OK. When is too much K too much K? So that's a weird thing. So I am not aware of any recommendations with a cap on potassium fertilizer rates except the ones I developed in North Dakota recently. Some states are moving toward that direction right now, giving suggestions and insinuating there's a problem. I'll show that at the end, but we're the only one that caps the rates. And this is very new to me, because when I was a young agronomist 40 years ago, sometimes we would apply up to 800 pounds an acre 0060 in central Illinois when we had a client farmer that bought land, and a lot of times the landowner farmer would mine it, for lack of a better term, of nutrients, and the K levels were really low. So the farmer wanted to build his potassium levels up to where it wasn't going to hurt his yield. And at the time, and there's still not, there aren't any restrictions on rate of potassium in Illinois. There isn't a too high rate. You can put on anything you wanted to. So we did. It just, cost money, but we never thought about crop problems. So I've talked about our potassium studies with Manbir Rakar and Amit Chatterjee and John Brucker that we did between 2014 and 2016, and it was a response to decline in potassium tests in southeast North Dakota, and high removal when people changed their rotation from the wheat-based, sugar beet-based to a corn and soybean rotation. And the common potassium soil tests in that region were 100 to 200 ppm commonly. which is very different than they were 3 decades ago. So we added more sites in 2015 and 16, but only over 29 of those rate studies, only half responded like we expected with the dry soil test, potassium test alone. So this is what it looked like. We had sites that we thought wouldn't yield very well, but they yield just fine with a low soil test. And then we had some with a higher soil test that didn't yield as much as what we did, and that continued for the 2015 and 2016 year. So it was pretty frustrating, and then we started looking at clay chemistry, and when we divided it out with a smectite to light ratio less than 3.5, then that described a suite of samples, a suite of sites very well. And when we had smectite to light ratios greater than 3.5, then it described other sites pretty well as well. And we increased our critical K level on those sites to 200 ppm, where before it had been this 150 ppm. So from a survey of the state, we have a map of the state that consists of at least 2 samples per county here West River, and 3 samples per county, and even more density down here where we did our studies. And so this is the map that we've shared with growers to help them with their potassium rates, to try to figure out if they're okay or not. So the new recommendations are established with the higher critical level, with the high smectitic soils for corn, alfalfa, for sugar beets, for even spring wheat, durum, winter wheat. But toward the end of the project, we saw this at the very beginning, but didn't pay much attention to it because we thought we were doing something wrong. But we continuously found that once we got to about 200 pounds of 0060, that oftentimes the yield would tail off from that peak. If you put all of the sites, standardize all the sites to relative yield, and chart them out on this graph like we did here, that the peak is somewhere in here. It's not out here. It doesn't just keep going up. So it really does tail off. So out of all those sites, we had 2 sites that increased yield, a significant increase in yield when we applied 250 pounds of 0060 compared to the yield of 200 pounds of 0060. And that's potassium chloride for those of you that don't know that. But we had 5 sites that had a significant decrease in yield with the 250 pound potassium rate compared to 200 pounds of 0060. So that was new. So if we go to a return to K model, which is similar to the return to N model, in North Dakota potassium responses, and this is all generated in the southeast part of the state, is we increase our profit up to around 150 pounds of 0060 an acre, and then we decrease our profitability after that. So that, yeah, if we went to 250, we'd still get a higher yield than if we hadn't put anything on, but we would decrease our profitability significantly from what we were at the peak. So remember, the reason you put on fertilizer is to increase your profit, a farmer profit, and so putting on high rates tends to be counterproductive. So at a North Central meeting in Iowa here a couple years ago, this came up, or I mentioned it in my talk, that it was just kind of curious. And my colleague Carrie Lebowski said, well, she'd seen the same thing in Wisconsin, but she just thought it was just something weird and never really thought much about it. So this is their profitability of 7 years of broadcast applications of P and K to a field with an initially low soil test. This is north of Madison at their research farm at Arlington. So their most profitable rate of potash at these different phosphate levels from 0 to 90 was 120. generally. If you look and then compare the 120 K2O rate, that'd be 200 pounds of 0060 to 160, which is about 250 pounds of 0060. Here we get a profitability decrease at this rate, decrease at this rate, an increase at this rate. Well, it's the same. The A's are the same. And then a decrease at this rate. So 3 out of the 4 subplots, they had a decrease in profitability if they increased from 200 pounds of 0060 to 250. And at this site, at this different site of experiments, they had a profitability decrease, they had a profitability decrease, here it increased, and here it stayed the same. So 2 out of the 4. So 3 out of the 4 and 2 out of the 4, 5 out of the 8, they had a decrease in profitability. So they've seen it also. So it's not just us. So our current North Dakota potassium recommendations, if you paid attention in our corn circular, we cap the rate that you use in any given year at 200 pounds of 0060 per acre. And that maximizes the profitability within a year. So other states have also seen a similar thing, not so much in corn, but certainly in soybeans. There's some movement, especially well, you think about people in this state. In other states, there's no soybeans after soybeans, but we're kind of unique on that, and hopefully we're getting away from that. But there is fertilizer put in front of soybeans in some states. And so in work that Dan Kaiser's done in Minnesota, he sees anytime that you get the 0060 rate above 100 pounds, when you spring apply, you get a decrease in soybean yield that can sometimes be substantial. And in Indiana, they see roughly the same kind of thing. So what they recommend in Indiana is even before corn and certainly before soybeans, they recommend moderation in the potassium rates to not go too nuts on the rates. And certainly Dan Kaiser is urging a limit of 0060 ahead of soybean. Why this is happening, I think it has to do with the salt content. Minnesota doesn't see it so much in corn. They do it in soybeans, but we see it in corn. And I would assume that if we tested soybeans, we'd see it too. But our fields generally have free salts in them already. They have a soluble salt content that other states to the east of us don't have. So even a low salt test for us would maybe be 0.2, 0.3, and we commonly have ECs up to 1 and sometimes beyond that. So if we add a salty fertilizer like potassium chloride to the mix, chloride is a pretty active salt. Maybe that's why we're seeing the reduction. I don't know. But we seem to be okay up to 150, 200 pounds, and then beyond that, it can be a problem. So that's my presentation. I'm sorry I can't be there in person, but I suppose it's my fault. But I can't be there. So if you have some questions, shoot me an email or text me or call me. Here's my contact information, and thank you for listening.